Hi, welcome back. So we're in chapter 6, prediction by RCC at the outline prediction by regression, to discuss the outline of multiple linear regression. So far we have established the idea surrounding the concept of simple linear regression, which actually involve two particular variables, that is x, for example, and y. But having you understood this simple linear regression idea, it's easy now to expand that to k number of variables, not only x, but we can actually literally write this form here, y in terms of, again, 1 alpha 0, because to decide that the intercept of y, which most of the time called the bias, plus of course then you're going to take the alpha 1, x1, then alpha 2, x2, and all the way perhaps you could go up to alpha k, xk. So it doesn't really matter, stop at a particular dimension of x. So if we just graph here a 3-dimension, so it's easy to see in 3-dimension here. So the idea, once again, a value of x1, a value of x2, and we're going to tell you what is the value y looks like. So y is equal only alpha 0 plus alpha 1 x1 plus alpha 2 x2. In this case, the alphas is going to be responsible to actually account for this prediction is going to be alpha 0, alpha 1, and alpha 2. In the case of one variable, it was aligned, but here we're going to get a plane, looks like this. And once again, we need a mechanism again to quantify the quality of such a model or assumption of multiple linear regression in this case. So the point is not going to change by taking this RSS actually, and then every yi, this guy here, subtract that from the y hat. So the y hat is going to be equal to this equations represent that plane, taking the square and once again take all the summation. So nothing has changed at all. And the point is now we need to minimize that error. This is the only difference, of course. And by the way, to quantify the fit of that prediction, again, we're going to use r squared. In order to minimize the error, how can we rewrite this in a form that can be quite a bit more explainable? First of all, let's look at the y hat, alpha 0 plus alpha 1, x1 plus alpha 2, x2 plus all the way k dimension we could have. So I want to generalize that. Now, this form from linear algebra perspective, what is it? Well, we got alpha vector, which is equal to alpha 0, alpha 1, alpha 2, all the way to alpha k. And then I got the x actually is going to be a matrix end of the day, because you're going to get the x1 and x2 from different number of equations. So if we want to actually multiply this by the dot product between this vector and this matrix, if we transpose this, it's going to be 1 by k. A number of values, right? And we keep the x as it is. In this case, we got like k by 1. We're going to end up with a singular value, which is going to be the y hat, the predicted value. So in this case, what we could do, actually, we could rewrite the y hat, alpha transpose, multiply by the x. If this is only y hat for one point, a certain n, where n is which point are we actually predicting. So my RSS, that's going to be y, the original y, of a certain value of n, for example. Subtract that from the value of the y hat. We're going to take the square, and at the same time, we take all the sum. So what we did, we just transformed this RSS into the form of a kind of a matrix thing. Okay, this one, I just expand that summation in the form of a matrix. But we need the square term. E transpose E, you're going to end up with exactly this term. I could rewrite this, the RSS. It's easy now to take this one for a derivative purpose. But before that, let's actually expand a little bit. This is the final format. Take now the derivative in terms of this alpha. This alpha, don't forget, this represents all the vector of alpha 0, alpha 1, all the way to a number of alphas anyway. In the RSS, okay, derivative in terms of the alpha vector. This is the minima. Final things, if we'd like to check also the r squared, let me tell you what's the formula of that. 1 minus, called the MSE, divided actually by variance of the y. So what is this MSE? Actually, it is the RSS but divided by the n. We call it actually the mean square of errors. Now I think the best thing to do right now, a real example, we have got 96 rows, 5 dimensions here of data set, and we would like to choose one of these variables and predict in terms of the other. In total, we can take maybe 3 of these variables. One of them will be the dependent and the other will be the independent. So we can take the AP, APT, and the APD1. I have decided just to graph descriptive analysis model, as you could see here, with all the variables. So here we got the AP variable seems to be normal at some point, although they are like some squeezing kind of maybe gamma distribution at some points. And we get the APD. Well, APD is not bad. Side of distribution. APD2 as well. Well, most of the variables seems to have some kind of a normality. Now, if I want to take actually a quick describe on these 3 variables all together, you could see here the count of them. As we said, we got 96 cases. The mean of the AP is this one, the standard deviation, minimum, maximum, percentile, etc. Also, maybe we can look at something related to the correlation actually between them. I just wanted to see whether there is correlation or not. If you look at the AP, of course, correlated with itself with 1, but if its correlation with APD seems to be positive with 77, so it's a quite strong correlation. The stronger happens to be with the APT, so both of them happens to be a good predictor. But also you could look at the relation between the APD1 and the APT itself here. The relation is even extremely strong. I mean, it's 95% correlation. We are doing good. Let's say graph now. I'm going to do 3-dimension, of course. This is X, this is Y, and this is my Z. We know our model should look like the normal equation, as we discussed before. This guy here, right? It's going to be alpha 0 plus alpha 1 x1 plus alpha 2 x2. So this is the data as it is in 3 dimensions. So this is the X, this is the Y, and this is my Z. It's obvious to have that linearity is that when we investigated the correlation positively, we have some here kind of, maybe I could consider them an outliers, but still it's hard to, I mean, segregate the entire data set based on that. But if we manage to fit in a plane here to like kind of account for this data set, we are doing a great job. And that's exactly what I wanted to create, actually, a fictitious plane. Just let's assume a 99 over 25, and here maybe I could assume a value of 0.99, and I'm gonna fit them in a plane to see how they would look like inside the real data set and see what the plane would look like. So it's completely illogical to see this plane gonna be a good predictor anyway, because you could see it's completely out of the line. Now we need this plane to be exactly crossed through these points, and we wish actually this kind of point to be on the plane. That means we are doing a very good model to fit the data. So what can we do? This is the point. We're gonna minimize the RSS. So here we're gonna calculate through this function called the RSS function. From this line space, what I'm going to do, we're going to present 2D of the RSS. So we're going to draw that parabola, then the hyperbola. Let's just start with the parabola. So basically I took RSS vector, and then I create a range in the alpha 10. So we're going to have like 200 values of different alpha 0. Basically what it does, it take the alpha vector where we create 2 vectors from alpha 1, one value, from alpha 2, another value. So we got 2 different line space because each one of them I wanted different alphas. Create this vector with 2 values, which is going to be the first input here for the RSS function. And then I assume also a value of alpha 0 from the alpha 0 line space. So pass all of that to the RSS function, and it will return for you a value of the sum of square of error. Take that error, append to this RSVV. And what you do basically, you just try to calculate the minimum of that RSS vector. This minimum value will represent actually where the alpha 0 was the best, with the minimum value alpha 1 and alpha 2. But that doesn't mean it is the best, because it depends on our luck of choice of these alphas lying here. Now we can create a 2D figure. Also, I can draw now the hyperbola. So we need to make a mesh grid of both line of alpha 1 and alpha 2 and to capture the z. The only difference here, I had to actually fix the alpha 0 manually. I didn't want in every point in the measure grid different alphas. And then finally, just to graph it again in 3D. You should be able, first of all, to see the best alpha, which is actually represent this point here. So if you look at actually the hyperbola, and what we are trying to reach out is the minimum, the kind of a plane touch into this mesh grid, which is actually correspond to this point here. So basically what I can do to test whether these points really look like good or not, let's get back to this plane that we fictitiously assumed. These are the values that we have just captured. Exactly as we expected, this is a perfect plane, seems to really fit the data very well. So this didn't happen by chance, but happened with a methodical way of following the procedures we are doing right now. The choice of the alphas of these line space, for the alpha 0, for example, the alpha 1, this point between 2 and 3, alpha 2 between -1 and 0. Actually, I was aware of that from the very beginning. Before that, I have chosen actually a different values, and it gave me again a parabola like that, and I captured the minimum, but actually the model still was very bad because my choices of these alpha was completely random. That's why we needed actually to minimize that RSS using the minimization problem that we discussed earlier. So manual way of doing that is transpose A, the inverse of that multiplied by A transpose Y. Alternatively, you could use this built-in function from NumPy. Grant both. They are exactly identical values, as you can say. So we have now the best alphas, and that's if we go back and fit them again, as we said. So you want to try also, you can choose different alphas within those range and make sure you are still on the same line. I did that, and you could see that we are actually at the same exact point. So we got a test data set here, the last 10 cases or 6. And by the way, those cases were not involved in the trainings. We are not aware of their real Y's. You could see I make a percentage to show you. So the first, there's a 3.3% error, 15% error, 2% error, almost 0% error. I was very close here, 2, 3. So it's a quite a bit good model. I mean, maybe the point at 15 was somewhere from these values. That's why we're not captured them good. The others were okay somewhere here. Now, finally, you could also test the good of fitness using the R squares. We set the formula of the MSC. You get 83.38%. That means this is explaining almost 83% of the variation between each point and its mean. So that's all what you have to know, I think, in terms of simple or multiple linear regression. How about if the data set is not really going to be linear? I think that's exactly what we shall discuss next. I will see you then.